Good morning everyone. So here I am going to record a lecture on Introduction to Semiconductor Physics, and this lecture is in the continuation of my last lecture, and it is lecture number 4. So in the previous lectures what we have covered about Schrodinger wave equations and applications of different Schrodinger wave equations are the potential well, the infinite potential well, potential barrier and electron in free space. So now I am going to discuss about what is electron in periodic lattice and how it is situated in the periodic lattice. So as we can see from the diagram that there are circular type of structure is here. So there are 4 circles are there, and the electrons can exist anywhere in this circle. So the number of electrons in the innermost circle is 2, then number of electrons in the second circle is 8, then 18, then 32. So energy of bound electron is quantized, only discrete value of electron energies are all allowed. So we have already discussed in the last lectures, previous lectures, about the Pauli exclusion principle. So what is Pauli exclusion principle? So Pauli exclusion principle says that no 2 electrons can have the same energy state. So every electron must have different energy state. So every electron must have different energy state. No 2 electrons can exist at the same state. So we can see here that the electron sitting here, the number of electrons are 2 here and number of electrons are 8 here. So we have the different electrons at the different energy state. So only discrete value of electron energies are allowed, and the wave function of the 2 atoms will overlap, that is the 2 electron will interact, which will result in discrete energy levels. So we have already discussed about discrete energy levels. So these are the energy levels for the conduction band, and these are the energy levels for the valence band. So we can draw a diagram showing for the single atom. So for the single atom, if we draw, it's like this type of a structure which shows the probability of electron in a particular state. So the probability will increase first and then decrease radially for the single electron or the single atom. Similarly, when we use multiple atoms or more than one atom, so if we use more than one atom, so there will be some overlapping like this. So this region is overlapping region. So as the atoms come closer to each other, it is in close proximity to each other, then there will be overlapping with the exponentially decaying function like this, the probability of the electron existing in the particular state. So this probability is basically called probability density function. This probability is called probability density function, and it is represented by P of R. So we find that P of R versus R is directly proportional. As we increase the radius, the probability of having the existence of the electron is going to decrease. So when 2 electrons or atoms close together, then there will be overlapping between these probabilities densities. So we can see from here that we have K, L, M, N type of states. The shells are there. For the innermost shell, we designated it as K, then the outermost is L, then next is M, and then next is N. So according to the value of the K, L, M, N, we will see what is the state of the electrons. So next, same, what is allowed energy state? So there are several allowed energy state which combine together to form an energy level. So once we have the valence band and the conduction band. So as we have discussed that in the conduction band we have energy states, and in the valence band we have also energy state. So these are the allowed energy states in which the atom can exist. Allowed energy states in which atom exists. So the difference between this valence and conduction band is defined as Eg, which is called as band gap, and for silicon, this band gap is around 1.1 electron volt, and for germanium it is around 0.6 electron volt. So we can see that the band gap for the silicon is higher as compared to band gap for the germanium, which are basically the elemental semiconductors. We already discussed in the previous lectures the elemental semiconductors. So these allowed energy states enter into the atom. These energy levels are having various electrons of different energy. So these energy levels also split into allowed energy state. You can see from here that I have splitted the energy state, the conduction band and the valence band, into allowed energy state. So the atoms will reside in these only in these energy state, the allowed energy states, and it has a discrete value. So the first point is it has discrete value, and the atom is in allowed energy state. So these 2 point discrete values of energies, and the atom can exist only in allowed energy state. These 2 points are very important for the purpose of how the atom will reside or how the electron will reside in the allowed energy state. So next, what we can show here from this figure, you can see that there are two energy states, E1 and E2, and the atoms are initially very far apart, and when they are come closer, they will interact with each other and there will be some overlapping between the energy states. So here the first structure, that is E2 and E1, the higher energy level is E1 and the lower energy level is E2. When the atoms are at 0 degree Celsius or 0 Kelvin, you can say, that is at temperature 0 Kelvin, it is far apart, the atoms are far apart. But when they come closer to each other at 200 Kelvin for silicon, we have a M-shaped type of structure, like a V-shape or a M-shaped type of structure, you can say, or the atoms come closer and the wave functions will overlapping with each other. So here what is going on, that the wave function, as we have already discussed in the Schrodinger wave equation, that psi x comma t for the Schrodinger's wave equation. So this wave function psi x comma t will overlap. So overlap when two atoms come close together. When atoms come close together. So here we can see that the band gap is around 1.1 electron volt at 200 Kelvin, and initially it is high band gap or at 0 Kelvin, and when the atoms will come closer, the band gap will reduce and it becomes at 1.1 electron volt. So this is for the silicon structure. Usually we can also draw for the germanium structure. So these red stripes will show the allowed energies for the atoms to reside in particular energy state, and this diagram showing the crystal structure of the single silicon, as we have already discussed about the crystalline silicon. That what is crystalline? Crystalline means that the atoms will be in a regular fashion. So atoms are in regular fashion. They are not at random. So in the case of as in the case of the amorphous, they are randomly arranged in a particular lattice. They are at a particular periodic arrangement is there in the case of the crystalline silicon. So this is periodic arrangement. So you can see that one atom is here, then second atom is here, silicon, third atom is here. So it's kind of a periodic arrangement, not a random fashion. So next, the splitting energy levels. So how can the energy levels will be splitted? Or initially it is not splitted, but after we increase the temperature, it gets splitted. So as we have already discussed that the semiconductors conductivity we can vary according to the doping. According to the p-type doping or n-type doping, we can vary the conductivity of the semiconductor material. So these splitting energy levels are present in the atom to form a separate energy level. So we can see that initially the energy level is single, but after some time it gets splitted and there will be a change in the energy band gap. So here the energy band gap is very high, this energy band gap, but as the energy bands will get splitted, the energy band gap reduces. So these energy levels have specific energies of their own kind. These have particular energies. These energy levels are actual position of the charged particle where they reside. So as we already discussed that Pauli exclusion principle, that no two electrons can exist at the same energy state. So we have the different electrons at different energy states, and they are properly arranged in a valence band or as well as in conduction band. So in the valence band we have holes, and in the conduction band we have electrons, like this. So the holes are basically vacancy created by electrons. So as the electrons will move from the valence band to conduction band, there will be vacancy created in the valence band, and which is called as holes, and electrons are basically in the conduction band. So once we apply some physical or some external energy to the electrons in the valence band, it will move towards the conduction band, and the number of electrons in the conduction band will keeps on increasing. So here we have seen how the bands will get splitted. Now what is the purpose of taking semiconductor materials like arsenic? So like we have already discussed about gallium arsenide. So this gallium arsenide is a material which is used basically for gun diode, and it is a kind of a direct band gap semiconductor material. So we have arsenic or arsenide type of crystal having a 5 angstrom interatomic distance. So interatomic distance is the distance between the two atoms. So what we call as interatomic distance. For the case of the arsenide, between two arsenide atoms, it is around 5 angstrom. So as in the first structure, it is around 5 angstrom, which is properly arranged atoms. Arsenic is properly arranged in a form of crystal. But if the arsenide is arranged in a random fashion or in a amorphous type of structure, or we can say free atoms are there, in that case the interatomic distance will get increased and it is greater than 5 angstrom. So next what we have the hydrogen atom. So the hydrogen atom is basically the atom having one electron in the outermost shell. From the figure you can see itself that the hydrogen atom has only one electron at the outermost shell, and it has an atomic mass around 1.008. So hydrogen atom is analyzed by scientists due to its simple structure, as there is only one electron at the outermost shell. There are various equations involved in the analysis of the hydrogen. We have already see about Schrodinger wave equations in the last lecture, or with that lecture we have already seen about two types of Schrodinger wave equation for the hydrogen atom. We can also analyze that is time independent and time dependent, and time independent. This is time dependent, or time independent is usually called as position dependent. So two type of equation we have already discussed for the Schrodinger wave equation, and for the hydrogen we can similarly analyze these equation for the Schrodinger wave equation. So next what we have, the important thing, that how the hydrogen atom is arranged in a crystal lattice. If we are taking hydrogen atom, so the values of n for different energy state is n is equivalent to 1, 2, 3, 4. We have taken different energy state, then the possible values of L are 0, 0, 1, 0, 1, 2, 0, 1, 2, 3. For each energy state we have different values. For n is equivalent to 1, it has 0 value. For n is equivalent to 2, it has 2 values, which is 0 and 1. For n is equivalent to 3, it has 3 values again, that is 0, 1 and 2. Then for n is equivalent to 4, it has 4 values, that is 0, 1, 2, 3. And we can easily designation of the subshell is there, that is 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d and 4f. So according to this designation, we can write down the value of the hydrogen atom, that 1s, 2s, 2, 2p, 6 and so on. So the possible values of M1 for the hydrogen atom is 0 for the n is equivalent to 1, and for 2 it is again 0. For 2 having 0 value of the possible value of the L, it is 0, but for 1 it is 1, 0, -1. Then for 3 it is again 0 because the value of the possible value of L is 0. Then again for 3 is equivalent to, for particular value of 1, the possible values of L is having the values, 3 values are there, that is 1, 0, -1. Similarly for 2 it is 2, 1, 0, -1, 2, and so on for the fourth. So the number of orbitals in subshells are, for n is equivalent to 1 it is 1, for n is equivalent to 2 it is 0, because it is 0, that's why it is called as 1, only one element is there. Then 1, 0, -1, it is totaling 3. Then again for 0 it is 1, for 1, 0, -1 again it is 3. Then 2, 1, 0, -1 and -2, it is 5 elements are there. Then 0 it is 1, then 1, 0, -1 again it is 3. Then again 2, 1, 0, -1 and -2, 5 elements are there. Similarly for 3 it is 3, 2, 1, 0 and -1, -2 and -3. So total elements are there are 7. So we can see the number of orbitals in subshells and then the total number of orbitals in a shell. So total number of orbitals in a shell, we can add these two. So initially it is for n is equivalent to 1, the total number of orbitals in a particular shell is 1. For n is equivalent to 2, it is again 4. Then for n is equivalent to 3, it is 5, 3, 8 plus 1, 9. Then for n is equivalent to 4, it is 1 plus 3 plus 5 plus 7. So 4 plus 5, that is 9, plus 7, that is around 16. So these are the total number of orbitals in a particular cell of the hydrogen atom. So this table is mostly give you the idea of how the hydrogen atom is situated in a particular lattice and its energy states corresponding to n is equivalent to 1, 2, 3 and 4, and what are the total number of orbitals in particular shell. So total number of orbitals for n is equivalent to 1, 2, 3 and 4 can be easily calculated with the help of the subcell designation, possible values of M1 and the number of orbitals in subshells. So next, coming to atomic bonding. So as we have discussed the hydrogen atom, so there are different type of bondings are there. So atomic bonding is defined as the forces of attractions or the repulsions between two atoms. So there are different type of atomic bonding. The first one is the ionic bonding. Here the transfer of electron takes place between metal and non-metal atom. So the next one is the metallic bonding. Here the sharing of electrons takes place between two metallic atoms. So if there are two metallic atoms, there will be a sharing of electrons and it will form a metallic bonding. Next is the covalent bonding. Here the sharing of electrons takes place between two non-metal atoms. So what we have got that in the ionic bonding, we have one metal and one non-metal atom. In the metallic bonding, both the atoms will be metallic type, metals. And in the covalent bonding, we have two non-metal atoms. So we can see from the figure here that electrons transferred between sodium chloride. For example, it's NaCl. So in the case of the NaCl, Na plus or Cl minus, there is ionic bonding. There is ionic bonding. In the case of the copper, second one is the copper. In the case of the copper, which is particularly a metal, so between two coppers there are metallic bonding. The third one is the water, that is H2O or diamond, so which are non-metals and thus there are covalent bonding. So this basically figure shows how the electrons will be transferred between one metal and one non-metal and between two metals and then again between two non-metals. So these bondings are very much important for the case of how to calculate the mass of the particular atom or the effective mass of the particular atom. So next what we will going to cover that what are the different imperfections in solids. Obviously there are some imperfections in solids. The first imperfection is called as vacancy. So whenever there is a missing atom in a lattice, it is called as vacancy. So there is missing atom in lattice, there is extra atom in the lattice, it is called as interstitial. So the first figure shows the particular crystalline type of structure where the atoms are regularly arranged, but with the blue portion we have shown that there is some missing atom. So the missing atom will be your vacancy. The second one is having the arrangement is proper, but there is some misalignment in the third line or in the fourth line. So whenever there is some misalignment and there is some extra atoms in the lattice, it is called as interstitial type of imperfection. The third one is the line dislocation. In the line dislocation, there will be no regular arrangement. Some are there regular arrangements and some don't follow that the particular line of the arrangement. So it is called as line dislocation. The fourth one is the plane dislocation, and the plane dislocation is basically the particular lattice or the crystal structure has been divided into different planes, and all the planes have regular arrangement of atoms. So this type of deficiency or imperfection in solid is called plane dislocation. Plane defect. The line dislocation is different. So next one is the volume defect, and in the case of the volume defect, here the atoms are collected unwantedly on the surface of the material. So when there is any unwanted material on the surface of the particular atom, then it is called as volume defect. So these are the different type of imperfections in solid. We have studied that vacancy, interstitial, line dislocation, plane defect and volume defect. So next, how to add impurities in a particular solid. So there are two types of methods to add impurities in a particular solid. The first one is the diffusion and the second one is the ion implantation. So diffusion is what? Diffusion is the process in which the impurities move in the material from the region of high concentration to low concentration. So you can see from the figure that what is diffusion. There is some high concentration of atoms in a left side and there are low concentration of atoms in the right side. So the impurities will be added from high concentration to low concentration, you can say it will move from high concentration to low concentration. So this is called as diffusion. The second figure will shows the arrangement or in the glasses that the water, pure water, drop of dye. So when there is pure water or then there is drop of dye, so pure water has low concentration, but when you drop a dye, it has a higher concentration. So dyed evenly dispersed water. So when you put a dye in a particular water, it will disperse it and there will be a low concentration of the arrangement of the atoms. So we can see from this figure that the particular type of impurity which is called as dye here. So dye is the impurity here. Dye is the impurity here and the pure water. So first element is dye, which is the impurity, and the pure water is there. So when we put dye plus pure water, obviously there will be some dispersion. Dispersion means there will be some broadening in the water. So the atoms, the dye particles or the dye atoms will move here and there will be some low concentration type of arrangement which you can see from this figure. So there is so the impurities will move from high concentration to low concentration. This is high concentration, this part is high and this part is low concentration. So this is called as diffusion. The second one is the ion implantation. So ion implantation is the method of in which the impurities are injected at a very high velocity in a particular form of ion into the lattice so that the lattice surface breaks. So we can see from the figure here that there is a lattice surface and implant damage and inactive dopant is there when there is a ion implantation. So this is ion implantation, high speed, high velocity. Ions are injected here. So high velocity ions are injected from the top to the surface of the particular dopant, and there will be a change in the arrangement of the atoms in the particular lattice. So later on the surface is repaired back in order to get the same lattice back. So there will be some changes in the lattice and we have to see what will be the changes in the lattice, how to recover that lattice, particularly when there will be some ion implantation. So this is a implant process. So normally we use silicon dioxide layer on the surface, and the ion implantation is there with the silicon dioxide on the silicon dioxide surface. So ion implantation on silicon surface. So this will give you the overall idea about how the impurities we can add in a semiconductor device. So when we increase the impurities, there will be a change in the conductivity of the semiconductor devices. That's why semiconductors are very important as compared to metals and the insulator. There we cannot change the conductivity of the particular metal or the insulator. We cannot dope any impurities inside the metals. So we can easily dope impurities in the case of the semiconductors, and we have these two types of adding impurities method, like diffusion and the ion implantation. So next we have electron configuration. So the most stable electron configuration is the one in which electrons in orbital with lowest possible energy. So firstly we have to arrange the atoms in a lowest possible energy, then we assign the atoms to the higher possible energy, and so on. So when all the electrons in an atom have the lowest possible energies, the atom is said to be in ground state. So when the atoms are in the ground state or having the lowest energy state, so it is called as ground state. When electrons move to an orbital higher energy, this is referred to as the excited state. So as we have already discussed in last lectures also, so this is valence band and this is conduction band, and electron move from here to here. So from the lower energy state to high energy state or intermediate stages. So that stage is called as excited state. So whenever you excite some energy in the form of the light or in the form of the photon, the atoms will excite from the lower energy state to high energy state, from the valence band to conduction band. So these are the electron configuration. So next we have the Kronig Penney model. So before going into the Kronig Penney model, we have already discussed about the overlapping of the atom. So there are two type of forces we have, that is interatomic forces we have already discussed, but between the atoms there are some internal forces and some external forces. So when there is a single atom, only single atom is there. So in the case of the single atom, we have already shown that if this type of probability density function you will get according to the atomic distance, and when there are multiple atoms or more than one atoms, you have this type of structure which is having some overlapping region due to two atoms. This is for two atoms. So in the same way we define Kronig Penney model. So this is probability density function versus R. In the same way we define Kronig Penney model for the potential function. So this V is basically potential function. So we can see from the first figure that the potential function V is equivalent to 0 is the reference line, and V R is inversely proportional to 1 by R. So this is very important. The potential function is inversely proportional to R. As you increase the radial distance, the potential function gets reduced. So as we increase the radial distance, the potential function gets reduced from both the sides. So this is for the single atom we are showing here, and E1, E2, E3 and E4 are the discrete energy levels for the particular band, for the conduction band as well as for the valence band. Similarly, in the figure B, we can see here that if there are more than one atom, so if there are more than one atom, the potential functions will get overlapped. This is the overlapping region. This is the overlapping region. So there are some overlapping between the two potential functions of the two particular atoms. So this is atom 1, atom 2, atom 3 and atom 4. All have some potential function and they get overlapped. So the net potential function. So this diagram number C, is basically for net potential function. Net potential function. So the net potential function is defined from this to this, from this to this, as the, if we discard the overlapping region. So the net potential function is like this, like this. So we have drawn in the C diagram that the net potential function and the energy levels for a particular atom, and this net potential function, with the help of this net potential function, we can easily analyze our Schrodinger wave equation. But Kronig Penney model is the extended version of this net potential function, and it is drawn like this, Kronig Penney model. So we just reduce it to a rect type of function like this, and it has some value, that is 0, a plus b, and similarly minus b or minus a plus b. So with this we can reduce it to a particular type of rect function, and with the help of this particular rect function, like Vx is defined as potential function is Vx plus a plus b. So here we define for the Kronig Penney model Vx, which is Vx plus a plus b, the net potential function. So the potential function of single atom was drawn having a specific energy level as shown in first diagram. Then in the second diagram it is for multiple function, and the net potential function is shown in the last diagram. And with the help of the net potential function we can draw for the Kronig Penney model, where the potential function V of x is defined as V of x plus a plus b, where a is the interatomic distance between the two atoms. So this is called as Kronig Penney model. With the help of this Kronig Penney model, we can easily analyze our Schrodinger wave equations applications also. So next we have the expression of the Kronig Penney model, which is d by square psi upon d by x square plus 2m upon h cut square, E psi is equivalent to 0. And similarly d by square psi upon d by x square plus 2m upon h cut square, which is same as the Schrodinger wave equation, E minus V psi is equivalent to 0. This is for 0 to a and this is for minus b to 0. So these two equations shows, the equation number 1 and 2 shows the Schrodinger wave equation analysis for the Kronig Penney model. So the next topic for today's lecture is EK diagram. EK diagram is basically energy versus propagation constant. K means here propagation constant. Propagation constant. So EK diagram is basically energy versus propagation constant, or propagation constant is same as wave number. So we have already discussed about K, which is wave number is 2 pi by lambda. It is also called as wave number, or it is also called as momentum diagram, in which there is arrangement of energy in the periodic lattice of the silicon atom. So we have discussed about first the different type of semiconductors. So there are two types of semiconductors, direct semiconductors, and the second one is the indirect. So as we know that in the case of the direct semiconductor, we have the conduction band and the valence band, means the valence band maxima and the conduction band minima is at the same value of the K, and the energy is dissipated in the form of the light. So we have the value of the K is same for the conduction band minima and the valence band maxima. So you can see from here this point and this point is at the same value of the K, this point. This is called as direct semiconductors. And example for this is gallium arsenide. Similarly, for indirect, we have different values of K. So the conduction, the valence band is suppose here, this is valence band, the conduction band is somewhat here. So the energy is dissipated in the form of heat also here, but there is some extra transition here, from here to this point, from atoms moving from this point to this point. There is some extra transition because it is not at the same value of the K. So this is your K and this is E. So it is not at the same value of the K. That's why there is extra energy required for the transition from of atom from here to this point. So the EK diagram is energy versus wave number or momentum diagram, in which there is arrangement of energy in the periodic lattice of single atom. So we have the arrangement of atoms in the periodic lattice of the single atom, and there will be transition of electron from the conduction band to the valence band when we input or excite or stimulate some light into it, and there will be some release of energy. So H nu is the release of energy. So H nu is the release of the energy, and there is some change in the energy because if we excite some photon here for movement of a particular atom from conduction band to valence band, so it also requires some photon, which is called as stimulated emission in the case of the lasers. So electrons will move from here to this place with the same value of the K, and it does not require any extra energy. But in the case of the indirect band gap semiconductors like this is indirect semiconductors. So in the case of the indirect semiconductors, we require some extra energy to make the electron transition from this point, from the conduction band to the valence band. So since the energy of the atom in periodic lattice varies in a step-like structure, there are Brillouin zones in the diagram which are symmetric with respect to origin. So we are showing in the figure that there is some energy band gap from here. There is a band. From here, there is a band, and there is some energy gap between these two bands, and again there is a gap between these band and the reference band, whatever the K value is there. So there is some first Brillouin zone which will be here from minus pi by a to pi by a. So from minus pi by a to pi by a, there is one zone. Then again minus 2 pi by a to minus pi by a, there is minus 2 pi by a, there is another zone. So this zone, first Brillouin zone is here, this which is shown in the figure. The second zone is from minus 2 pi a by to minus 2 pi a, and the third zone is from minus 3 pi a by to plus 3 pi by a. So this is called as Brillouin zones, and from here we can easily calculate the value of what will the distance between the two bands or the gaps between the two bands. So this is called as EK diagram, or we can easily say like that energy versus propagation constant diagram will give you an idea about whether the semiconductor is direct type of semiconductor or whether it is indirect type of semiconductors, and so on. So next we have the significance of EK diagram. So the significance, what will be the significance? As we have discussed that there is some conduction band and there is a valence band, and the band gap is this one, this Eg is the band gap, and there will be some release of energy. So there are some electrons residing on the conduction band which will move towards valence band, and it will create some holes. So this basically creates some holes here in the conduction band, and electron is moving from conduction band to valence band as we excite some energy here, H nu. If we have a stimulated type of emission, or if we have a spontaneous emission, there will be no requirement of energy. So there are two type of emissions are here, which is spontaneous emission, and the second one is the stimulated. In the case of the spontaneous emission, it does not require any excite, or stimulated emission, it requires excite. So we have to excite the atoms in the valence conduction band to move towards valence band, and there are some occupied states in the valence band. So from here to here it is minus pi by a to pi by a. This is the first Brillouin zone which we have already discussed here in the last slide. This is first Brillouin zone. So this first Brillouin zone shows the occupancy of the electrons in the valence band as the electrons will move from the conduction band to the valence band. So the EK diagram of a direct band gap semiconductor such as gallium arsenide we have discussed is basically important for the purpose of making LEDs or for the purpose of making lasers. So if we want to make or design a laser or a LED, a laser or a LED, we require a direct semiconductor materials, and the direct semiconductor materials which we have discussed, direct semiconductors are like gallium arsenide. So if we want that we want to design some LEDs or lasers, so we require direct bandgap semiconductors which have a EK diagram with the same value of the K for the conduction band minima and the valence band maxima. The EK diagram curves consist of many discrete points, with each point corresponding to a possible state wave function psi x that is allowed to exist in the crystal. So the points are so close that we normally draw the EK diagram relationship as a continuous curve in the energy range EV to EC. There are no points in the particular wave function. So we have this type of EK diagram for the gallium arsenide. But in the case of the alloy composition, as we have discussed, there are different types of elemental semiconductors, then compound semiconductors, then alloy. So what is alloy? Like AlX, gallium 1 minus X, and then arsenide. So AlX, gallium 1 minus X and arsenide, we have different type of EK diagrams. So for this purpose, we have the EK diagram like this, that the lower valence band is residing here, valence band. The upper conduction band is also here, conduction band, suppose it is called as gamma. So there are some levels of conduction band minima is situated here, and it is some situated here, suppose it is L or X. So with the value of the X, small x, the fraction of the X which we take, suppose it is 38% or 0.38. So for 38% it is Al 0.38, then gallium it is 1 minus 0.38, then arsenide. For this we have initially the EK diagram is direct. Initially it is direct semiconductor, but after some time as we increase the proportion of the X or the aluminium into the gallium arsenide, it becomes indirect. So there are some numerous applications where we see that the EK diagram is very important. So the alloy composition, if we are not taking care of what is the fraction of the X and for the aluminium and what is the fraction of gallium 1 minus X, then it becomes indirect and we cannot make our LEDs and lasers with that proportion. So we have to see that whether the LEDs and lasers can be made from these proportions or not. We have to see whether the 38% for aluminium is required for the direct bandgap semiconductors material. So the overall conclusion for the EK diagram is what we have the diagram, EK diagram, that the energy versus K diagram, and we have electrons residing in the conduction band, then the electrons movement from the conduction band to valence band. Firstly, the most important thing, that the first thing is basically the electrons have to move from the conduction band to valence band, electron movement. Then we have to see what will be the occupancy of the electrons in the conduction band, which defines the wave function. So wave function will define, which defines the occupancy of the electrons in the valence band. So we have to see whether there will be creation of the number of holes in the conduction band, there is creation of increase in the number of electrons in the valence band, and there will be release of energy h nu, and these conduction band minima and the valence band maxima must be at the same level. So then only it will be a kind of a direct semiconductor, otherwise it will be an indirect kind of semiconductor. And for alloy composition we have to see properly that if for the alloy composition whether it is properly fractional values have been taken or not. If we are not taking the value of aluminum, suppose we have taken the value of the aluminum as 0.5 and gallium again 0.5 and then arsenide. So it is like aluminum 0.5, gallium 0.5 and then arsenide. So this composition will make it indirect type of semiconductor. Normally, obviously, it is aluminum gallium arsenide. We think about that it is a direct kind of semiconductor. But if we taking the fractional value of the aluminum and gallium and it is 0.5, then it becomes indirect. So we have to be properly sure about the fractional value of the X also. So with this lecture, I want to conclude that what we have covered in this lecture, that how the semiconductor materials can be used for the fabrication process of the LEDs and lasers, how we have the different type of atomic bonds between the two atoms. There will be covalent bondings, there will be ionic bondings and different type of bondings. What are the different type of defects in the particular lattice, and how the there will be direct and indirect bandgap semiconductor materials can make useful for the fabrication of the LEDs or the lasers. Obviously, the indirect materials we cannot use for LEDs and lasers. We must have to use the direct bandgap semiconductor materials for the basic fabrication of the LEDs and the lasers, which are light emitting diode, and lasers is based on stimulated emission. That's why I have told you that there can be numerous type of technique we can use, like spontaneous emission. There will be easily from the conduction band to the valence band, or there will be some stimulated emission. We have to apply some energy to the electron at the conduction band, and then it will come to valence band. And that's the beauty of this EK diagram, that we have to see the fractional value of the aluminum also, as we know that aluminum is not a kind of a direct bandgap semiconductor material. So we have to see what is the fractional value of the aluminum which we are going to add with gallium arsenide. If it is around 0.38%, then it's okay, but if it is increased to 0.5 or 0.6, then there will be a problem. So in the next lecture, we are taking some examples of Schrodinger wave equation and see what is the intrinsic and extrinsic type of semiconductor materials, how these semiconductor materials are divided into these categories by the definition of the impurities, how we can add impurities to these semiconductors, and then we come to drift or the diffusion type of velocity equations for the semiconductor materials. Thank you so much.